In question 9, we're asked to draw an adjacency matrix. So A, let's have A here. It just goes once to B in this direction, A to B. A also goes to C. Put it down here. There's no 100% right and wrong here. A to C, A to D. D, what's D's relationship? D just goes to D, so I can put A to D maybe in this direction. A to D. And then A doesn't go to E. B just goes to C. B just goes to C. C goes to B once. It doesn't go anywhere else. D just goes to itself. You don't have to have an arrow on the loop, but you can put one on if you want. And then E goes to B. We haven't got E on yet. And that's just it. E goes to B, so we can have E here maybe going to B. And that's my adjacency matrix. Part B, we have this model and we have two strings. One from here to here and one from here to here. PQ is horizontal surface. Don't get confused. So we're looking to find the tension in the strings, and we're given the information that the participant is 90 and the string makes an angle of 60. So let's look at our forces here. Horizontal and perpendicular forces. So we have a 30-degree in here. So along here, we're going to have the tension in the string, T cos 30 over here. Similarly over here, we're going to have the same force. They're both the same. So this is going to be T cos 30. This one's going to be T sine 30. And along here, T sine 30. And coming down, mg. So we have, if we take just a diagram like this, force is going up equal my force going down, so 90g. And we're saying we have T cos 30, which is root 3 over 2 times T. Root 3 over 2 times T. So that's going to give me 90g is equal to 2 root 3 T's over 2. That's right. So 2 will cancel. So the tension in the string will be 90g over root 3. We're asked to find the extension in the strings. I misread it as just tension, so there is a little bit more to it. So Hooke's law comes in here. And Hooke's law is that the force is also equal to minus the elastic constant times S. This elastic constant is positive, so the force here, the tension, will be equal to Ks. So 90g over root 3 is equal to 221.4 by the distance covered, which is going to be, we want just the extension in the string. We could get just x and then have the 120 involved, so we can do that. Might just be a little bit easier. So what we look at is x, the original length of the string, x minus 1.2 is the extended length, so we'll use the x minus 1.2. So if I divide by 221.4, I'll get x minus 1.2 and it's on the other side, so I need to add, take this expression, add 1.2, and my calculator is giving me 3.500, so 3.5 meters for the extension in the string. A couple more parts to this one. In a second iteration of the model, the engineer decides that he wants to double the elastic constant. What effect will this have on tension? Well, we saw here that changing the elastic constant here, if that is a different number, it's not going to affect tension. It'll affect the length that the string is brought down by. But Obviously the tension will still be the same, the angles are all still the same. In part C, the engineer wants to design a roller coaster for a fun fair, and in the first iteration he approximates the car as a particle on the surface of a sphere. Okay, so we have the particles P, it starts at P, tell at a point P, so it's going to be at rest, and then it's going to move down to Q. So we have conservation of energy here. We call this the height of zero. So we're going to have a half mv squared. We're going to have mgh for my kinetic and my potential energies. So at the point P, this is what they're looking for here. At the point P, P is a height above the surface where we have h equals 0. So what is this height above? So we have this small angle A in here. So if I draw that right angle triangle, this is the radius of the circle. This is the angle A. So this one along here will be r cos A. So that's going to be the height there for Q. Q, we have it's going to have the same triangle, but it's going to have the angle B in it instead. So I'm just doing the diagonal in the wrong place. Q, here, got my radius. My angle B is in Q, so I have r cos B for the height above my line height equals 0. So at the point P, a half mv squared, it's at rest, plus mg by h, which is r cos A, will have to be equal to at Q a half mv squared. We don't know v, that's what we're looking for. We look like we're on the right track with our cos A and our cos B, plus mg by the height, which is r cos B. So if we multiply by 2 and divide by m, we're going to get 2g r cos A is equal to mv squared plus 2, so we have divided by m, plus 2 g or cos B. So 2g or, if I factor that out, I'll end up with cos A, and bringing across this guy, I'll end up with a minus, so minus cos B is equal to v squared. So v is equal to the square root of the expression above. We have, if cos A is 2 over 3 and Q is the point where the particle falls off, find the angle B. So Q, it falls off, so we're going to have a forces diagram at Q. So this is where it falls off. We have mg coming down. We want the force towards the center. It's going to be mg, this is going to be beta with alternate angles. So we're going to have mg cos beta, and we're going to have the normal reaction as well. So what have we got? We're going to have mg cos beta minus the reaction is equal to the force directed towards the center, mv squared over r. We know it falls off, so r is equal to 0. We can divide by m, and we can multiply by r. So r g cos beta is equal to v squared. We have v squared down here in a different format, so let's equate them. 2g r by cos A minus cos B is equal to rg cos beta. We can divide by rg, and then we'll just multiply it out. 2 cos A minus 2 cos B is equal to 1 cos B. So if I bring the 2 to the right, I'm going to get 2 cos A is equal to 3 cos B. We're given a value for cos of A. What were we given for the value for cos of A? Cos of A is 2/3. 2 by 2 over 3 is equal to 3 cos B. So that's going to be 4 over 9 is equal to cos B. And now let's get the inverse cos of 4 over 9. So B is equal to 63.6 degrees.